Good day, everyone, and once again we are back together. All right, so we are going to be looking at some acid and bases. So if you haven't subscribed, please just make sure that you're part of the family. All right, and let's quickly have a look at this question. Now, before I actually look at the question, please, guys, I want you to remember that acids and bases does not purely just consist of the long 8 mark questions, right? So please don't make that mistake, okay? Please make sure that you remind yourself of all the other sections that have to do with this section. It's usually out of 18 to about 22 marks, and you can score yourself some good marks in the process. Right, let's start with the first one. They say to us we've got a balanced equation that represents the ionization of sulfuric acid in water, right? So in step one, we've got all of that. So they're asking in 7.1, is H2SO4, right, sulfuric acid, a strong or a weak acid? So we know that sulfuric acid is a strong acid, and the reason for that is that it ionizes completely in solution, right? It ionizes completely. All right. In water, or you can say in solution. Okay. Right. Well, it ionizes almost completely, but of course, we'll disregard that. Okay, so they say write down the formulae of the conjugate acid base pairs in step 2. Now, note in step 2, what happens? HSO4 becomes SO4 2 minus. So, what did it do? It donated a proton. So, this guy would be the acid. So meaning that this guy would be the base, right? Okay. And now, in the reverse reaction, so we know that we are going to have H3O, right? When it goes to the reverse reaction, it becomes H2O. So this guy would be the acid, as is always the case, and that would be the base, right? So now, what did they want? They wanted the acid base conjugate pairs in step 2. So remember, you always take the acid on the one side, you pair it with the base on the other side. Okay. And of course, the other pair would be H2O and H3O. Right? So please remember, when you're writing acid-base conjugate pairs, what you should always keep in mind is that it's always the things that look the same, but just have the H as a difference, right? Not H as in HE, as in HH, hydrogen, right? HSO4 minus as well as SO4 2 minus. That's our first pair. And our second pair will be H3O plus and H2O. That's our second pair. All right. Now, the next question says sulfuric acid is diprotic. Write down the meaning of the term diprotic. So remember, it's able to donate. It's a substance that can give away, or that can donate 2 H plus ions. Okay. Right. In fact, I won't write all of that down. Gives away 2 hydronium ions. Okay. Right. So please write that in full. Okay. Right. The next question says write down the formula of the ampholyte in the above reaction. Okay. Now, what is the ampholyte, or which substance behaves as an ampholyte? You'll see that in reaction 1, if you take the reverse reaction, HSO4 gains a proton and becomes H2SO4. But in the second reaction, HSO4 minus gives away a proton, and in this case, it behaves as a base, right? So which one acts as an ampholyte? That would be HSO4 minus. Okay, that is our base there. Right, now let's go on to the next part of this question. So they say to us in 7.5, right, a pure sample of potassium hydroxide pellets, right, with a mass of 11.2 grams. Okay, and this is added to 0.09 moles of sulfuric acid with a volume of 600 cubic centimeters, right? They say it reacts according to the balanced chemical equation given below. Right, now firstly, what did they want? They want the initial pH of the sulfuric acid. So what we're going to do is we're going to calculate the concentration of sulfuric acid. Okay, please keep that in mind. All right, so we're going to calculate the concentration of sulfuric acid. So concentration is number of moles divided by volume, right? And we've got 0.09 moles of sulfuric acid, and our volume was given as 600, so that would be divided by 0.6. Remember, the volume should be converted to cubic decimeters. Okay, so that's divided by 0.6, and we get a concentration of 0.15 moles per cubic decimeters. Now, remember, what did we just find? We got the concentration of the acid, but how does sulfuric acid ionize, right? Or in this case, remember, it is a diprotic acid, so which means it's able to give away 2 protons, right? According to the reaction that we saw there, right? It reacts twice to give us those 2 hydronium ions. So what does that mean? The concentration of the hydronium ions, okay, which are the same as H3O plus, should be twice the concentration of our sulfuric acid, right? So H3O plus ions concentration should be 2 times 0.15. So this would be 0.3 moles per cubic decimeters. And so to calculate the pH, we're going to say this is minus the log of the hydronium ion concentration, right? And that would be minus the logarithm of 0.3. Okay, so let's find that out. That's negative log of 0.3, and I get 0.52, okay, as our pH, and that tells us it is quite a strong acid. Okay, so that's pH of 0.52. All right, so this is obviously considering complete ionization, right? All right, so they say to us we've got the percentage purity of potassium hydroxide pellets used is 80%. All right, so which means even in the mass that we have, only 80% of it is the pure potassium hydroxide, right? So now they say calculate the number of moles of pure potassium hydroxide that reacts with sulfuric acid. Okay, so we are going to take 7.5.2. Okay, now remember we said we've got 80%, so the total mass in this case is so the total mass is 11.2. So let's take 80%, so that's 80 over 100 times 11.2. Okay, so let's find that. Okay, so that's 0.8 times 11.2. So which means the mass of pure potassium hydroxide should be 8.96. Okay, so that's 8.96 grams, right? So now this is the mass of the potassium hydroxide that would potentially react, right? So that means I'm going to now take this and say, right, we're going to find the number of moles, okay? Mass divided by molar mass. And in fact, they said to us, calculate the number of moles of pure. Okay, so that's mass divided by molar mass, so which is 8.96. And so remember, potassium hydroxide, when we go to the periodic table, remember potassium has a molar mass of 40 grams per mole, oxygen that's 16, and hydrogen is 1. Okay, so we're going to add those up. We're going to get 57, right? So that's 57. That's our molar mass. And so remember, we added 40 plus oxygen plus hydrogen, right? That gives us 57 there. All right, so we are going to say 8.96, and this is divided by 57, and we get 0.16. Okay, let's round it off to 0.16 moles per cubic decimeters, right? So finally, 7.5.3, they're asking us the question, determine which reactant is in excess and hence state whether the final solution is acidic, basic, or neutral, right? So if you remember, the concentration of the acid was 0.15, and the concentration of, or rather the number of moles, in fact, why did I even use moles per cubic decimeter? Sorry, at 0.16 moles, right, of of potassium hydroxide, right. In this case, so we have the number of moles of potassium hydroxide as 0.16, okay, right. And now I want you to note the number of moles of acid were 0.09, right? But remember, so what I'm going to do is I'm going to just assume if we used up all our acid, let's say we used all the 0.09 moles, how much potassium hydroxide were we going to need, right? So the reaction is, for every 1 mole of H2SO4, right, you've got 2, or rather you need 2 of potassium hydroxide. So supposing that we use all the 0.09 moles, how much sodium hydroxide or potassium hydroxide were we going to need? So this would be x times 1, that's x, 0.09 times 2 gives us 0.18 moles. Okay, right. Now, what does this mean? Remember, x represents the number of moles that you were going to need with, so these are the number of moles of potassium hydroxide that you are going to need if you have to finish up all of the acid. Okay, right. So the number of moles of potassium hydroxide did not reach this number, right? So what does that mean? It means we will not be able to use up all of the sulfuric acid, okay? So as a result, it means there will be sulfuric acid that will be in excess. So in answering the question, we're going to say, well, the resulting solution or the final solution will be acidic, okay? So therefore, our final solution will be acidic, all right? Because the number of moles of acid that are required, or rather the number of moles of base that is required to react with the acid is less than what is required. Okay, right. That is how the cookie crumbles. Of course, you could have also checked using the potassium hydroxide. You'd still be able to see that the acid would be in excess, and so the final solution is acidic. All right, and that is how the cookie crumbles, ladies and gents. I hope that you were able to follow on this question and that you really thoroughly enjoyed it. Okay, otherwise, I'll see you guys again next time. Shop, shop.